సక్సెస్ఫుల్ చెప్తుందా?
మనం అట్లా ఏం ప్లే చేయలేమా? మరి సిస్టంలో ఉన్నది ఇక్కడ కనపడాలంటే ఎట్లా, వినపడాలన్నా కనపడాలన్నా ఏదైనా వీడియో ప్లే చేయాలి, అది ఎట్లా? ఇప్పుడు ప్రజెంటేషన్ ఇంకా వాళ్ళు తెచ్చుకుంటారు కదా పెన్ డ్రైవ్లో, అది అక్కడ కనపడుతూ ఉంటుంది కదా, అది ఎట్లా?
ఓకేనా? వస్తుందా లింక్ ఏంది గిట్ల ఉంది? ఫోన్ చేస్తారు ఏమన్నా ऑडियो के लिए छोटा है, वो लोग लैपटॉप एचडी में उधर तक है ना? हाँ उधर तक आ जाए लैपटॉप उधर लगा हाँ वीडियो तो प्रेजेंटेशन के
then he will start reviewing and then the questions what he puts in his video. That is what the traditional officer.
फर्स्ट వెనక
background light తీసేస్తే లైట్ తీసేసి అక్కడ రావాలంటే ఆ లైట్ ఆఫ్ చేయండి ఆ లైట్ ఆఫ్ చేయండి
ऑटो की स्टोर करेक्शन అక్కడ డార్క్ ఉంది. స్క్రీన్ షాట్ ఇస్తుందా?
Go 24x. Nothing again, sir.
హెడ్ఫోన్స్ ఉన్నాయి ఫస్ట్ సాఫ్ట్ ఇప్పుడు అది పడుతుందా? అక్కడ ఉందా? అందం
hello. Hello, hello. Hello, hello.
ఇది కొద్దిగా కవర్ పెట్టు इसको बंद करो इसको क्लोज करो लोग बैठेंगे बाद में भी 2 मिनट के बाद इसको ये प्लीज
Please. Good evening, ladies and gentlemen. Myself, Indra Venkatasu, on behalf of Smart Labtech Hyderabad, have pleasure in inviting every one of you present here for this evening seminar on rotating bed reactor, the RBR. As you all know, Smart Labtech, one of the leading suppliers of pharma laboratory instruments, have been supplying laboratory instruments in and overseas India. And we all have gathered here to attend the seminar this evening. And I welcome all of our valued customers from Dr. Reddy's, Arvindo Laboratories, Lawrence Labs, Sai Life Sciences, Arajan Life Sciences, IICT, Ion Exchange, Natco Pharma, Newland, Granules, Sun Pharma, Viatris, and I'm sorry if I have missed out someone's name. Thank you. I have pleasure in inviting today's chief guest, Dr. Emil Weisstrom, having traveled all the way 6,500 kilometers from Sweden to be present with us here. Smart Labtech has been associated with Spinchem AB Sweden since 2018 and involved in the sales, promotion, marketing and sales of rotating bed reactor and its related products in the Indian market. Now, not wasting much of the time, already we were behind schedule of about 35 minutes. I welcome our chief guest, Dr. Emil Weisstrom, and our eminent speaker, Dr. Padmaja, IB expert based at Hyderabad, and Dr. Bhargav Pandya from the R&D department of Sun Pharma, Gurgaon. Let us give a good warm welcome to all of them. A small intro of Spinchem. Spinchem's vision is to transform the world by providing the simplest, fastest, most stable and resource-efficient technical solutions as a catalyst for the global process chemistry industry. Spinchem is a dynamic and innovative company that is dedicated to providing world-class solutions to a wide range of customers. Located in the Uvilova Science Park in Umeå, Sweden, Spinchem is well positioned to take advantage of the latest research and developments in the field. Their team of experts, including both financial and scientific professionals, is committed to staying at the forefront of the industry and working collaboratively with academic institutions to drive innovation and progress. Now, I request our MD, Mr. P.V. Satyaprasad, to take this forward with these few words by addressing this gathering.
Thank you. Welcome to this great evening. I don't want to go into the details of welcoming again our guests of speakers who are sitting on the dais here. Just quick intro. Smart Labtech has been in existence in Hyderabad for over 2 decades, representing some international manufacturers of top class like Sartorius, Brookfield, Memard, you name anything, they are all either top 2 or top 3 range of manufacturers, which maintains a consistency in the quality and in servicing and rendering our services to all sectors of scientific fraternity, especially in the pharma sector, like the customers like Arabindo and then Dr. Laboratories, Natco, Hetero, Mylan, you name anything where they are existing. With the concept behind this, taking this forward, we have signed the contract with Spinchem in 2018. And this is not a commodity. Spinchem products is not a commodity where easily can be sold unless we understand the application and the utility of the equipment. Though it looks like a small rotating reactor and all, it's a size is small and then does very big things and all. So it has got enormous applications where Dr. Emil will be able to explain to all of us. And incidentally, he is not an entrepreneur who has started this operations and all. He is a researcher converted into entrepreneur. Right from the beginning of nut and bolt to the complete concept to product. So that is how he is able to answer, and he is able to give each and every point, whatever it comes across. And then he is also involved in a lot of R&D activities in method development, process development for various scalable activities and all. So before I close it, and then I strongly feel that this particular session where we have assembled here definitely will be able to give a more light on the spin-cave products and rotary, especially in the rotary bed reactor, and what kind of utility it is and what kind of application that we can. This applications of RBR is not limited to the library, whatever it is existing. It has got enormous thinking process. You can do it later stage once the product is in hand, and then we can do so many developmental activities and method developments and all. That is the reason why in the initial stages when we have signed the contract, immediately we thought that this is not a product of catalog selling, a product which need to be shown, which need to be demonstrated. We have kept this product in our application lab, and then so many demonstrations have been carried out, including in our lab as well as in the field activity. So looking at the product, people say that yes, this is the product worth buying it. Probably I think because of the capex or something like that, but that's a different story. But it's worth to see the product here, worth to understand the application of this particular product. Thank you, Dr. Emil, for being here, Bhargava, and then Dr. Prapacha. And then I leave the platform to the rest of the speakers. Thank you very much.
Thank you, sir. Next, may I invite Dr. Subramaniam Iyer to come onto the dais and just give a small intro of Neoscience Hub, sir. I request all of you to please take your seats down.
Good evening and welcome you all. Before we go into a hardcore chemistry and solid phase and all, I just want 10 minutes of yours to just give you some insight of what Smart Labtech does. There's something called Neoscience Hub. It's a new concept, it's a new magazine which is being promoted. So I'll just take you to the entire thing, how it started and what happened. Okay, there are about close to 35 to 40 scientific magazines in India presently. Okay, and these 35-40 magazines are positioned in such a way that they are either academic or they are totally driven by the corporate. Like if you take a look, the first one which comes to our mind, at least when I was in college and school and all, Science Reporter was something which started by CSIR and way back in 1960s. So it's almost completely 60 years. The content is excellent, but the only problem here is it is not being promoted well. So the students and all, many of the readers are not aware of this. So that's the reason. If you take a look, and then we come to microbios, which is given by the corporates, and cutting edge, which we all know of the SPINCO, that's also, it's more like, it's analytically given for whatever you do your work, you get published, and the same thing, the biospectrum more given by pharma industry. So there was certainly an unmet need here, where we said, yes, we need to have a magazine which is more like a coffee table, like a magazine which people will understand simple science, and they, because we are talking of Viksit Bharat now, like 25 years, unless the next generation starts understanding the science and all, it will not be easy for us to go to that level. So when Mr. Satyaprasad met me and he had this vision, I immediately laughed because I have a plan, I enjoy writing, okay, right from beginning. So I said, okay, let me take this up, apart from the other technical responsibilities. So I'll just take you briefly to what it does. Science Hub basically is a monthly science magazine, popularizing the science. It has only science but science, nothing else. Okay, and this has been registered under the Newspapers Act because it's not easy to get. You have to undergo a lot of scrutiny by the government of India unless it's not like a cakewalk. We spent quite a number of months, almost close to a year, till we got, because this is given by the Delhi government. So it's not easy to get, but we could get it. And then our trademark is also, the name and the logo is also being approved. The Neuroscience Hub and the logo is also being approved. So in all ways we are complying to all the requirements of what a magazine, what has to be done. Every 5th of the month, as per your RNI, you're supposed to declare to the government when are you going to publish. And the date is 5th of every month. That means 5th is the sacrosanct date. You can't go later or you can't go earlier. And that's the level of, they expect compliance of that. And along with this, there's also a web portal. Because now slowly, it's going digital. So there's also a web portal which complements this. So we have a web portal and an e-magazine, which is, once anyone clicks neurosciencehub.com, he or she will actually get all the issues and all the videos which is posted. And a complete dedicated team is there. Maybe later on I'll tell you who all it is. So what's the difference between other science magazine and this magazine? The main thing is the cover story. The cover story is actually the pulse. It decides. Every month the team decides to have what should be a cover story. And the cover story generally based on that month or that period, what should be done. So if you see a cover story, they are mostly hot scientific topics. It's nothing like, it's taken very seriously and a lot of effort goes into designing the covers. And also a lot of experiments which is conducted by all others is being captured here. And some can be controversial, some can be, let's say, not very compliant, but it's all captured here without any bias. And we also capture, the team captures interviews with scientists and all. And regulatory guidelines is captured for pharma industry because a lot of pharma industries, they don't have time to go to the regulatory guidelines. So this could be a quick thing for a quick look at that because it gives you a very succinctly the entire pharma guidelines. And there's a review section of scientific books and some of the films which are sci-fi films and all is also reviewed there. And we have tied up with the newspeak from IITs and IISCs and all for whatever they have new discoveries and all, we get a feed from them. So that's also captured here. And of course, we have a lot of theories about plants, environment and all, just to keep the audience moving. And questions and puzzles and all, question banks and all. So let me come to the portal. We have, the Neuroscience Hub portal is also there, parallelly going along with the framed one. And there are about close to 200 videos uploaded so far. We have over 1.82 lakhs, close to 2 lakhs viewers. We have 1,400 subscribers. And the best part is around 25 to 34 is we did some analytics of who all view our YouTube channel and all. We were quite surprised seeing that they are all young people who are actually viewing this. So that's something very encouraging for us. And I'll just play, Ashok, how do I click that hyperlink? Sorry. No, yeah, I'm getting. Yeah. Okay. We know this man, he's a born actor. Yeah. Volume. Okay.
keeps you updated on all current happenings.
Oh yeah, it's coming.
What do we cover?
Life sciences form. You don't have to be a nerd to know science or be a frog in the pond.
What is neuroscience all about?
It's a web portal. It's an e-magazine for common man. It brings science and technology on your phone. It makes science more interesting.
How does neuroscience help us?
It fosters novelty. It keeps you updated on all current happenings and answers all your whys. Why?
What do we cover?
Life sciences, pharmaceuticals, wellness, basic science and engineering. Current R&D happenings around the world. Interviews with scientists and eminent personalities.
What else?
Topics which affect citizens directly. Sections like quizzes and puzzles to rack your brains. And at the end, make science more fun.
Is it?
Always remember, science is not all the boring.
Visit Neuroscience Hub.
Let's go. Next one. E-magazine.
Neoscience Hub generation influences with our everyday lives in each area. Whereas generation is blooming with innovative minds. Suggestion, thoughts, and informative information in our day-to-day life. How technology is upgrading in terms of medical sector, agriculture sector, and environment sector. Have you ever thought that technology is blooming with our young scientists with their unique ideas, innovative minds? Visit us at www.neosciencehub.com or write to editor@neosciencehub.com.
Thank you, Ashok. Yeah. Okay, so that was just to give you a feel of how the magazine looks. Okay, we have some early readers of this magazine, G.P. Prasad of Dr. Abbey's and Mark Prasad of Shankar Biotechs, Dr. Kumar of Chemo, Jayesh Ranjan, Satish Reddy, and JNTU Vice Chancellor, and everything. Just to name a few, we thought we'll just tell you these are esteemed readers of this magazine. And as an editor, I enjoy certain privileges. I'm in the media and I get to meet people and all. And we also have been covered by television. Recently we had a show where we had one of the very exponent journalists who visited the entire country. He was there. So we had a media coverage. And I get to meet the Minister of Science and Technology, Sridhar Babu, and Mr. Acharya, who actually completely designed the entire high-tech city of this. My colleague Naresh Munna meets the MD of Chemo, and of course we met the JNTU Vice Chancellor, Dr. Narasimha. Nothing happened without a team. I've been nicely, and in fact all the smart work is done by them. I just give a presentation, and Naresh Munna is the managing editor, and he does all the designing and all. We have Aditya and Ashmi who does all the support system. And Karthik is the one who designs everything. I have a web developer, Kalyan, on board, Balakrishna, video editor, and photographer, and Naresh. So with this team, I do all that. Okay, thank you so much. Thank you.
That was nice. Thank you, sir. Thank you, sir. Now, moving next, may I request Mr. S. Kuppaswamy to come onto the dais and just give a short profile of Madam Dr. S. Patraja, please. Kuppasar, please.
assessment of our neuroscience of magazine. And welcome Dr. Padmaja. It's my pleasure to introduce you to this audience. Dr. Padmaja, I know her. We work together in Hyderabad Pharma. The founder, director, of CEO of High Proprietary Intellectual Property Solutions, has promoted this organization for providing services to various corporate and academic institutions in intellectual property matters. She is an IP expert actually. Dr. Padmaja is one of the first few intellectual property professionals in the Indian pharma industry with more than 25 years of experience, with Master in Chemistry from Hyderabad Central University, doctoral degree in Chemistry from Osmania University. She also holds a PG diploma in IPR and a law degree from Osmania University and is a qualified patent agent. She had also undergone training at renowned law firms in the US. Dr. Padmaja is a member on the board of Avishkaran, which is an incubation center promoted by NIPER Hyderabad to facilitate individual inventors and startups to get the benefits of the research facilities. She is also empaneled in the core expert committee of Telangana State Biodiversity Board. Dr. Padmaja has also been an active member of the CII working group on IP when the framework of Patent Act amendment was done based on GATT and TRIPS obligations. As a part of her previous and current assignments, she has the experience of handling both domestic and international litigations. She has deposed and testified in several of the ANDA related litigations in the US. She has also expertise in working with clients specialized in herbicides, fungicides, and other crop care products by way of filing, prosecuting, and defending their patents. She holds the expertise in drafting patent documents for different countries such as India, US, PCT, EU, CA, AU, JP. In total, she has the experience of drafting and filing over 2,000 patent applications. Congratulations. Thanks for accepting our invitation for this seminar as an honored speaker on a short notice. Over to Dr. Padmaja.
Thank you, sir. May I invite Dr. S. Padmaja to please come onto the dais. Please come now. Okay.
So, good evening. I think we are late and but it's final. So, I'm privileged to be starting with my presentation, though we have other technical experts speaking to you a little later. So, I understand we are looking for a lot of challenges in the industry, being in the development and then manufacturing side. So we all know there are a lot of challenges in research, manufacturing and other areas from technically, but I am focusing on a different challenge which generally all the developmental scientists face. Manufacturing side, it's already technology is developed and constantly for manufacturing, but the technical experts who are the development side like Pranya and other people know what are the challenges when they face when they have to develop a technology which has to be transferred to a manufacturing site. So that is the challenge from the intellectual property side. There are many aspects of intellectual property, but I am focused main on patents, because especially from API industry, the patents are the one which are very important. When it comes to finished dosage form, there are other aspects of trademarks and trade dress which they have to look at. But from API perspective, the patents are something which we have to look at. How do we move forward? This is going to be. So, I'm going to focus on general issues from IP perspective. As we mentioned, so we all know that there are a lot of challenges from when you look at development and manufacturing. There is regulatory compliance like developing the product as per the systems and SOPs, or maybe COA which is required as per the guidelines which are there in different markets, and then plans to be complied for audit purpose. Then we have reagent suitability. When we are developing a technology, there are a lot of reagent suitability. Some reagents may be there for CROs like clamps and other things, which may not be used when it comes to API manufacturing. So there are restrictions which have to be looked into. I'm not focusing on those angles. And the availability of equipment, which we're going to look at different equipments maybe in the next presentations. So I'm focusing on the IP challenges which are faced generally. So what are the major issues when we look at IP challenges? That is patents which are having different expiries in different countries, and the suitability of API for all the markets. So this is the one which I'm going to focus. When you develop a technology, a process or an API, whether it is suitable for all markets or not. If it is not suitable, why it is not suitable? So these are the two questions which we're going to understand in the next few slides. I'm not going to take much time, with some live examples which we are facing currently. So why, if at all, if they're not suitable, why they're not suitable? Generally, we have different types of patents. It's not one patent which is covered for one product, it's different patents. That's one issue is the product patent, which is called API patent or bulk substance patent actually. So which is the one which is the major block. So suppose if most of us, as we see the names which are called for in the introduction or maybe, most of us are in generic industry. So since being in the generic industry, we have to look at the target launch date, like when you want to launch commercially. You might be developing for the regulatory filings like DMF or ANDA, but when it has to be commercialized, the date which is the launch date. So when is that is the product patent expiry. When it is, each one would have its own expiry. Each one would have its own expiry in different countries with different dates, which I'm going to show with one example. So why that is important is the drug substance, that is the API, that our bulk drug is covered by that patent. So if you're launching before that, you would be infringing on the patent which is covering that molecule. What happens if you're infringing? You're dragged into a lot of lawsuits in different countries, and lawsuits in different countries will take years to be settled or resolved for you to see the light of the day to launch a product. So to avoid lawsuits is to look at is the best option, whether are you able to do it every time or you have to do some other options though you invite lawsuits. So the best thing is to wait for the drug substance patent, that is called product patent, and then you have, as a process chemist, you will have lot of processes to manufacture the API being covered by different process patents. Each product or each molecule would have many patents to be covered by the processes, because each molecule can be synthesized in multiple routes. Each route would have different variations of reagents, solvents, conditions. Each step would have multiple variations again. So all those aspects would be covered by one or more process patents. And another challenge which we generally face is the polymorph patents, that is crystalline form, amorphous form. So what is that is a technical expert would be knowing, being in the field, but the crux of it is each product would exist in multiple forms, whether those forms are protected by patents. If they are protected by patents, when they are expiring, whether they are expiring before or after this product patent or process patents. There could be either ways actually, either ways in different countries differently. And then we have salt patents. So for example, sitagliptin phosphate, sitagliptin hydrochloride. There are many examples to take like that. So when are they expiring? Whether the commercialized salt is expiring later or before. And then particle size patents. This is another challenge which an API player would face. That would have implication for a formulator as well, that is finished dosage for manufacturer. So when the particle size is restricted, the same API with some restriction in particle size may not be suitable for a formulator to have a better dissolution and disintegration. So you should play around with the particle size as well. but there are restrictions from particle size patents. So what are those restrictions actually? And the requirements for a generic player to be like API manufacturer to be precise is like you should look for product patent, or sometimes there are indication patents which would block the generic launch. So we have to look at expiry, that's the best option. Or if you have some grounds to invalidate, that is knock off the patents, revoke the patent. So then you should try for invalidation, but which is very difficult in case of a product patent. So you have to wait or look at invalidation options for launching. And then you develop a non-infringing process. Non-infringing process is because sometimes the innovator, the best possible process which can be used for manufacturing a product must have been covered by an important patent which expires later. So then you are forced to develop a non-infringing process which is not infringing that patents which are expiring later. How do you do that? Your science should be able to help in developing non-infringing process. And then you should file a master file and FDA approved facilities. So these are some minimum requirements for you to play around as an API player. When it comes to a formulator, there are different types of sets of guidelines and then checklists which have to be taken care. But with respect to API, at least these minimum things have to be looked into for developing a product and commercializing it. So this I would like to take with some example so that we connect to the scientists who are sitting here actually. So this is an example for a product which is called empagliflozin. What are all the previous setup things which I've mentioned? I'm showing with an example which is with empagliflozin. Many of you are familiar with because everybody, 99% of the industry is working in, at least in Hyderabad and other industries. So, and then which is having a lot of challenges. So that's the reason I picked up this example. Right from process point of view, polymorph point of view, and each country has its own challenges with respect to this molecule. So what is this slide talks about? This is an API. The API patent is expiring. I've looked up 3 countries, but this matrix can be extended to hundreds of countries actually, because the patents are protected in hundreds of countries. And there are cases where we have done the matrix for hundreds of countries for different set of patents. So here the empagliflozin product is expiring in the US on August 1, 2028. That means if somebody wants to launch a generic product for empagliflozin, you should be launching in on, that is after this August 1, 2028. But whereas the scenario when it looks as EP, that is going beyond actually, that is May 2029, few months later. So we have to wait for launching in EP in May 2019, whereas the product can be launched in August 2028. And then the product can be launched in March 2025 in India. So this set of same empagliflozin, the launch date is different in different countries, but this may not have implication. But these dates have implications for a process chemist. So what are those dates? There are some set of intermediates which in turn leads to the empagliflozin are covered by some patents. Indirectly, it also covers the process for making empagliflozin, which may be the best process developed by the innovator. So what did they do is they protected by different set of patents which are expiring on August 17, 2028, August 17, 2028 in US, whereas it is expiring on May 10, 2026 in EP, and the same day, May 10, 2026 in India. So what is the significance of these dates? Suppose, if, I said this is one of the best possible processes developed by the innovator. This process can be used maybe with a 17 days lag to commercialize immediately after August 17, 2028, the empagliflozin product. It can be used for commercialization in the US, but there is a rider, quote and unquote, 17 days difference is there. Somebody is ready to wait for 17 days delay in launching empagliflozin in the US, they can wait and use the same intermediates, same process which is protected by this patent. And the same way it can be used for Europe as well, because this process patent is expiring before this product patent. Because as I said, we generally wait for launching after the product patent expiry. So this date is earlier than this date. So hence you are able to do it immediately after the product patent expiry. Use the same process which is done by the innovator. But when it comes to Turkey, this is TR is Turkey here, a part of EP, there is an exception. Turkey being in the European market, there are set of rules of regulations are different. Still, even though it is there, because there are certain things that are not applicable to Turkey. So same empagliflozin, it is expiring in March 2025 instead of May 2029, where in the rest of the other countries it is in May 2029. So if I have to develop empagliflozin for Turkey, what is the challenge? The challenge is we have to develop a non-infringing process because product patent is expiring in 2025. The process patent is expiring 14 months later. So we want to wait for using the innovator process 14 months, or you have to develop a non-infringing process. There are people like customers from Turkey, they want an empagliflozin to be launched immediately in March 2025. The reason is the first launches would have a big icing actually, not the cake. So they can eat the icing, otherwise the cake will be left out. So since the pricing, everything would be important, the customers means the finished dosage form manufacturers. So they want empagliflozin produced by a non-infringing process so that empagliflozin can be launched in March 2025 instead of May 2026. So here you are forced to develop a non-infringing process to get the commercialization immediately in March 2025. Similarly in India, same scenario in India. So if empagliflozin has to be launched in March 2025, which we have seen in the last few years, the day one launches in India are in big way. Or sometimes at-risk launch are also there actually. At-risk launch means before product patent expiry, before a specific product patent expiry, a lot of Indian companies are launching at risk, inviting litigations in India. That's a different one. But if you're waiting for launching after product patent expiry, again, there's a lag of 14 months for an important process. So again, you are forced to develop a non-infringing process, at least to get the benefit of having early commercialization that is on in March 2025. So is it so easy? Sometimes it may not be easy to develop a non-infringing process because you have other challenge. Other challenge is a commercial challenge. The commercial challenge, we already have discussed a few minutes back actually, maybe half an hour back, that day by day, the commercial challenge is big. That means your pricing, the cost of the API is very important, and there's a lot of competition in reducing the cost of API. And to be sustainable in the market, you have to be giving your API at a competitive price. So is it so easy to develop a non-infringing process at a competitive price? It may not be working out every time. It may not, because we have seen the cost and CC is also calculated with the non-infringing process. Sometimes it may not work. So what is the option left out? To have the icing in the first place, that means to have a benefit of a first day launch immediately in March 2025 in India or March 2025 in Turkey, you can have a non-infringing process at a different price, at a higher price, with a specification matching to the specification of this process. If you are able to map it, then you have a benefit of having a process which will immediately enable you to launch and change or switch wherever it is possible. Again, a change of API route of synthesis is not that easy because it calls for a lot of regulatory challenges, but as long as you're able to comply, it's best way to do a dual strategy of having different processes for different markets, different processes, for different launch dates. So that's how we should be able to play around with our process engine. And if you see the drug master files and CEP's file generally, every company would have multiple drug master files with infringing and non-infringing or whatever processes, because as it is said, it is a continuous development. As you have improvement, it may not fit into the old drug master file, so you are forced to file another drug master file and go for change variation. So this is how you should be able to playing around. And the same example of empagliflozin, now I'm looking at polymorph perspective, because as I said, every product have multiple challenges. And all products may not have similar challenges. Sometimes it differs actually based on the patent situation or patent scenario surrounding that molecule. So same example of empagliflozin with polymorph perspective. Here we have the empagliflozin product patent, again same dates, August 2028, May 2029, March 2025, and crystalline form, which is expiring in April 2027 in the US and in May 2026 in EP, but again it is later in Europe. Again, one more exception is Turkey again. So this is odd man out in Europe. Most of the products in Turkey has this challenge. So if you're looking at product development for Europe, and if you have a customer based in Turkey, be cautious and in developing a product which is a process which is non-infringing, because most of the product patents are expiring. Most means 99% of the products will expire in Turkey early, whereas in the rest of the Europe, it will expire few years or few months later. So if you are looking at a process which is after this by May 2029, you are going to lose out this market. So are we ready to lose out that market is a question mark which the company has to decide. If they don't want to lose out, they are forced to develop again a non-infringing process. As I said, similar scenario in India. So most of the time, Indian expiries and Turkey expiries match. Whereas US and rest of the Europe, rest of the other 40 odd countries, Europe have different expiries. So if you make a map of this, again, few exceptions, little later expiries like Switzerland and other countries would have different expiries. It might be little later. So all those exceptions have to be looked into. The reason is, the moment you launch a product with an infringing product or infringing technology, you will be inviting a lawsuit. Coming out of those lawsuits in those countries is not that easy, because you have to put a lot of resources as small players in defending those lawsuits. You have to defend and come out of the lawsuit. You have to put in monetary resources as well as the personal resources by defending technically, because the lawsuits are technical based, process based, and polymorph based. So you need a lot of resources which can be used in developing new products. So this is one of the challenges which we generally see that. And the same, similar data, which, as I said, if you have US product patent August 2028, process is August 17, 2028. This is again important date, April 15, 2027. So that means the polymorph which is covered in this patent can be used for launching the empagliflozin product in August 2028, but there is a lag of 17 days, a difference of 17 days per process. So there are companies who doesn't want to take that risk of losing that 17 days as well. The reason is, many of you must be looking at first to file concept in a paragraph of challenges. And if you are somebody who's API supplier for a company who's looking at first to file ANDA filing, they don't want to lose this date as well. They want an API suitable for August 1, 2028. They want that. Because one day is also big money in generic industry, especially for blockbuster type of products. So we have to play around as scientists, our technical experts, in developing a product which 99% of the cases, with my experience of 30 years in the industry, I have not seen any process, any polymorph, a single process catering to all the countries. Very rare cases where we see a single process will cater to all the countries wherever your company is interested in commercialization. So that's the reason we should have multiple processes developed in the first place based on the strategy of the company, in which countries they want to launch, in which countries you have a customer base. So based on that, you focus initially and develop it. Or you have to come back for the same product which you have developed 5 years back, 10 years back. Come back again and redo the same molecule where you might be having interest or not interest, but you have a customer base. If you are able to plan it in advance, make multiple processes with your current resources. You don't need to revisit the same product again, wherein that same time can be used for developing a new molecule. Because every day we are getting new molecules. So that resources can be used at a later date for that. So this is how it looks like, and the same example, how it looks like in EP, which we discovered when we have all dates together, because if we keep all the dates together, we'll get clarity. So that's the reason we prefer making tables, especially in the launch planning actually. So as I said, Turkey we have to have a different process, whereas for the rest of the Europe you can have the infringing process and the innovator process and innovator form. This is one of the biggest challenge molecules. There are many molecules like this which have similar challenges where you are forced to develop. And if you look at Japan, if you look at Korea, if you look at Australia, their expiries are much more different. So, and then the challenges again are much more different. Actually, you are forced again to develop a different process in those countries. So this is again in March 2025 in India, 26 and 26. So again, you are forced to develop a process for 14 months. Otherwise, you lose your customer. Customer will not buy your API, though your product is developed, process is developed, tech pack is there, and then you have taken expert batches. Your DMF is filed, CEP is filed, or EDMF is filed. But the moment, if it is for Turkey, they will not take your process with this process which is covered in this patent because they want to launch March 2025. So there's a lot of chances of refusal by the customer. So that's the reason we get a lot of customer queries, whether your process is infringing, non-infringing, what is the polymorph data, does it have any contamination? Contamination is a different story which analytical people will look at. But contamination is also important from polymorph perspective. So why contamination is important, which analytical people will look into is from IP perspective, intellectual property, patents perspective. Contamination of a form, like especially in this case crystalline form, should not be present in detectable limits in a non-infringing form. For example, you might look at amorphous form in this case. So the crystallinity should not be detectable limits by any technology. I agree, like Dr. Pandya would be able to tell that because he must be facing a lot of challenges there. So how do they detect? A lot of analytical tools, and new analytical tools are coming up actually. So that's a big challenge of not having a contamination of infringing form and a non-infringing form. So, particle size is the biggest challenge. Here I'll just go to directly one example. Usually D90 less than 89 microns is the innovator claim. BMS has claimed that. And then immediately a lot of third-party companies come up saying that D90 above 90 microns, D90 above 100 microns. So the latecomers, that means late entrants into apixaban would have two challenges. That is, one is in non-infringing this, but when you're trying to non-infringe, you step on somebody else's patents. So this is again the biggest challenge. So early entrants would try to protect that other non-infringing option because even third parties are filing patents. Generic companies are also filing patents. They are protecting their own process patents. They are also protecting their own particle size patents. So if you see around particle size itself, at least few patents would be there for apixaban. Few patents, not one. So same way in other areas. So how do you make that particle size is a big challenge. If you're not meeting the particle size specification, you might be having a liberal spec in your COA, in a spec for particle size limits, but the formulator who's a buyer from you would have a lot of challenges. So this is one of the challenges which generally we face in the API industry. And how to circumvent and interpret the claims? Sometimes use different solvents, conditions to do different route of synthesis. How do we do that? Look for prior art. Look for prior art, that is before the second that later patents. Because there must be a synthesis existing for that product. So if you are having that prior art, though it may not be commercially feasible in all angles, still try to develop it for some time and then make engineering process later. And then look at claim limitations where we as experts help actually. What are the claim limitations for each patent? Are we able to overcome the claim though there is a patent? There's possibility sometimes. So these are the things which we look at and help the scientist. And with this, I'll close. Any questions? Maybe we'll take up after the session because the speakers are waiting. Is that so? Dr. Deepu? We'll take okay, if they have any questions, we are ready to take now itself. Good. So there you go. Thank you.
Thank you, ma'am. Now, may I invite Mr. Swami to please give a small intro profile of Dr. Bhargav Pandya, please.
Welcome Dr. Bhargav Pandya from Sun Pharma R&D Gurgaon. It's my pleasure to introduce as a second honorable speaker to this audience. Dr. Pandya is Senior GM, Head Flow Chemistry R&D Sun Pharma Medical Industries in R&D Gurgaon. He holds PhD degree Organic Chemistry having more than 23 years of experience in R&D. His interest lies in the field of complex molecule synthesis, polymorphs, biocatalysis, new technology development, flow chemistry, CRAMS and technology transfer for continuous production. He has number of publications and patents to his credit. We wholeheartedly welcome our honorable speaker Dr. Bhargav Pandya to this seminar. He will talk on sustainable manufacturing in pharma, a life cycle approach. Over to Dr. Pandya.
Thank you, Dr. Cook. Thank you, Dr. Kapu, for the nice introduction, and Dr. Dharma. Today, I am going to talk on green chemistry practices in pharmaceutical industry. It is in line with our today's topic, that is sustainable manufacturing, pharmaceutical life cycle approach. If I will talk about global chemical outlook, which was published by United Nations in 2019, the chemical industry is one of the major contributor for air and water pollution. It accounts almost 3% of the pollution, green energy related gas emission problem. Furthermore, WHO estimates that air pollution, including pollution from chemicals, is responsible for the approximate 7 million premature deaths every year worldwide. Chemical production, due to this various innovation has came and new technology progress in various industries has came from agriculture to medicine. However, the environmental impact of chemical products is growing concern. We continue to rely on chemicals to meet our modern needs. It is important to carefully analyze and address the environmental impact. If we look at the overall chemical industry, it can be divided into 4 major categories: oil and refining, bulk chemicals, biochemicals, and pharmaceutical industries. As we go from the oil to pharmaceutical industries, the production scale is highest in the oil and refining, and it decreases in the pharmaceutical industries. But the E factor, which is the indicator of the wastage generated per kg of the production. It is lowest in the oil and refining, while it increases from bulk to fine to pharmaceutical industry. It is highest in the pharmaceutical industries. It is because of the very complex nature of this particular industry. Green chemistry, if I will talk about a simple definition, green chemistry is the utilization of set of principles that reduces to or eliminates the use of generation of hazardous substances in the design, manufacture, and application of chemical products. So, green chemistry is about waste minimization at source, design and chemical synthesis which can avoid the such type of wastage, use of catalyst in place of reagents, so the reaction should be catalytic in nature, use non-toxic reagents wherever possible. We shall avoid using toxic reagents and we shall find out alternate ways. Use of renewable resources, improved atomic efficiency, use of solvent-free or wherever possible use recyclable or environmentally beneficial solvents, minimize hazard, increasing safety. Paul and John in 98, they have coined this green chemical principle. All the people working in the India industry are aware of this, and they further improvised their definition, their criteria in 2010. I will not talk much about it. Strategies to achieve green chemistry goals are avoidance of late stage resolutions, because if we do the resolution at the late stage, 50% of the chemicals used in that manufacturing of that particular product are called waste. So we shall, if required, and it is commercially viable, then we should do early resolution. Increase the number of genuinely telescopic steps. When I mean say genuinely telescopic steps, that means number of steps when we synthesize, we shall not isolate those intermediates. Not only isolate, I mean to do the workup and then instead of drying, then you can use the wet material. Not like that. We shall avoid the workup, because in workup, lot of chemicals, solvents, aqueous waste are being generated. Increase the number of steps carried out in water, and in particular the number, for example, enzymatic reactions are generally being done in water-based solutions. Introduce more efficient intermediate isolation like direct drop processes where you can efficiently isolate the material. Use technologies to reduce solvent usage. For example, a centrifugal extractor, rotary disc contractor are helpful in reducing the usage of solvent considerably. Use technologies for efficient manufacturing, for example, continuous manufacturing, sonocrystallization, rotary bed reactor, reactive distillation. Those type of equipments or technologies will help pharmaceutical industries to overcome many challenges. So one of the sonocrystallization is actually helps in reducing the particle size, which we are not able to achieve through a crystallization process. At Sun Pharma, we are focusing many fields. Out of that, green chemistry, green solvent, biocatalysis, asymmetric synthesis, reaction in aqueous medium, process optimization to minimize the wastage, increasing the yield, newer technology like usage of boric acid reagent for amide coupling, flow chemistry are the focus area. Today, I will talk about three areas, that is green solvent, biocatalysis, and flow chemistry. I will start with the solvent. So, in pharmaceutical industry, when the products under concept, it starts from the enzyme molecules which undergoes various studies, from the efficacy to phase 1, phase 2, phase 3 studies. In the early phase, when the product is as an NC is taken for the efficacy studies, at that time medicinal chemistry, the usage of solvent is highest, and it keeps reducing as the product moves in phase 1 and 2. Then at that time the process is getting optimized, and by the time the product completes the phase 3 and reaches into the commercial phase, the usage of solvent is reduced drastically. And then the generic players comes, they started the solvent recovery also, and they helped the industry overall to reduce the usage of solvent. Further, industry is targeting to reduce the usage of these solvents. These are the choices of solvents, green chemistry solvents. The best choice are in table. The reasonable are in orange or yellowish color table, and there are the solvents which are not usable. Out of that, I can say dichloromethane still people are using, and dimethyl formamide. Still people are struggling to replace those solvents. Just to show you an example, if the process has a usage of pentane, hexane, they can be easily replaceable with heptane. Heptane is a higher boiling point, and it can be easily recovered and minimize the losses. Diisopropyl ether or ether can be replaced with safer solvent like 2-methyl THF or tertiary butyl ether. TCM can be replaceable by ethyl acetate, tertiary butyl ether. Toluene also sometimes works. 2-methyl THF like solvents also works. So these are the solvent choices we can, switch over from the toxic solvents. I will show you some case studies where I have myself worked upon at Sun Pharma. The first one example I have taken is the amide formation. It is an intermediate of lumacaftor. In this particular process, the process is the amide is being formed from the difluorobenzyl diazoxide carboxylic acid through acid chloride formation and followed by the coupling with the amine to make the amide. The reported reaction is in DCM, and through a few optimization conditions, we got a quantitative yield through this particular route. However, we deliberately tried to find out alternate solvent instead of the DCM. So we find out that the toluene works very well and it gives similar yield and quality. Not only that, during the scale up there is a challenge. We have faced that during the reaction there is a dimer impurity formation due to the presence of oxide chloride, which easily can be overcome by toluene, because in process we can little bit recover the toluene and it can eliminate the oxide chloride, and it can help us in reducing that dimer impurity. So we don't face that particular challenge while scale up. Another example is the alkylation reaction. This is saphenamide intermediate, where if you can search the literature, you can find out solvents like toluene, ethanol, acetone are usually with various phase transfer catalysts and potassium carbonate as a base. Although toluene is not that toxic, ethanol is very green solvent. So we still tried, is it possible to do this reaction in water? And we came out with a good condition. Although I am not presenting many conditions here because of the restriction of our pharmaceutical industry. The reaction works very well in water, and we get the similar yield. Another example I have took here is the synthesis of this glucofuranoic acid. It is an intermediate of one of the complex carbohydrate molecule. It's a pentasaccharide, part of pentasaccharide molecule, where I worked upon this molecule. The synthesis starts from the diode. In the first stage, the alcohol was protected using Vidamus chloride, followed by the production with acetic anhydride, and then in situ deprotection and oxidation using chromium trioxide reagent, and then further hydrolysis to get the desired molecule. It is a 5-chemical transformation step. A lot of toxic solvents are being used to DCM 2-stage pyridine. Toxic reagent like chromium trioxide are used there, and overall yield is 50%. So we thought, is there any possibility to do the synthesis of this particular carboxylic acid? What actually we are doing? We are doing here is the oxidation of a primary alcohol in the presence of secondary alcohol, right? So we went into the literature and we find out that tempo-based oxidation conditions are reported where this particular transformation can be possible. So we worked in the lab and we found out one good condition where the tempo and engaged oxidizing agent, which is not toxic as chromium trioxide, in mild base and THF water, this condition works very well. So in the previous process we got around 50% yield, here we got 55% in single step, direct function. So a lot of toxic solvent has been eliminated. toxic agents, and the most important part is the E factor. Lot of wastage has been eliminated in this particular group. Then I will talk about biocatalysis. So advantages of biocatalysis are the reaction, the nature of enzyme is such a way that they are regioselective. They can distinguish between distant functional groups. They are enantioselective as well. So they recognize the pro-chirality of the substrates. And enzymes are even chemoselective. They react on a single type of functional group in presence of the other. They follow all those 12 green principles. I will skip this. So many transformations can be possible nowadays using the biocatalysis reaction. Possible. For example, enzyme can oxidize the primary or can oxidize the alcohol to ketone. It can even esterify the alcohol. It can reduce the ketone to alcohol or through ketoreductase, or it can convert into directly amine, desired amine through transaminase, or it can oxidize even. It can oxidize the sulfide. It can demethylate. It can hydroxylate the double bond of the aromatic double bond or dihydroxylate. It can form amide from the amine. It can hydrolyze the amide reverse reaction to make the amine through amidase, and it can convert again to ketone. Like similarly, I talked about the ketone to amine. Similarly, it can convert directly amine to ketone using transaminase. It can hydrolyze the ester, or it can esterify the carboxylic acid. It can hydroxylate the terminal alkyl group. Enzymes can do hydrolysis of nitrite to amide, or further to acid. Even it can add water to the double bond ammonia. It can convert into epoxide, and it can even reduce the double bond. So nowadays, many enzymes are available, but the problem with enzyme is they are substrate specific. So we have to do a lot of work. We have to find the right kind of enzyme, and nowadays many companies are coming up which they are genetically modifying those enzymes. I will touch upon 2 case studies. Again, myself, I have worked on those case studies. Atorvastatin. So, atorvastatin, Rinvaxi has won the Terraform challenge in this particular molecule, which Dr. Padmaja has just recently talked about. So, atorvastatin synthesis has 2 main raw materials. One is the diketone, another is the side chain. There are a lot of synthetic schemes are reported to make the side chain. It can be started from the ketoester, or it can be started from the chiral pool, and for the glycan condition to extend the chain elongation, followed by boron reduction, reduction. So a lot of toxic chemicals are being used in this particular group. More than that, the overall quality is very poor. The molecule is in such a way that purification is not possible. So it has a very high challenge. So people have worked on this molecule, and there are 2 major routes are reported for the synthesis of this particular cyanoketal. The first route is the ketoreductase route, which starts from the acetyl ester. Using ketoreductase and glucose dehydrogenase, the first hydroxide, the ketone is reduced selectively into the desired chiral alcohol. Then the substitution reaction of chlorine with nitrite can be was done using the halohydrin dehydrogenase, followed by the interconnection reaction, similar which was done in the previous chemical synthesis, followed by again selective reduction using ketoreductation and glucose dehydrogenase to get the diode, which was then further protected to get the cyanoketal, which can further used for the making atorvastatin. Another route was reported is from the chloroacetaldehyde and acetaldehyde. The first stage is making the lactone using aldolase and glucose dehydrogenase, followed by ring opening using tertiary butanol to make the diol, and further using the hydrogen dehydrogenase, we can substitute the chlorine with the cyanide nitrate, and then further protection. In this particular case, the diol can be further utilized for the corrosive stitching as well. So this particular keto reductase group was developed by Codexis. So this Codexis has done this innovation, and the route has excellent selectivity, and in each and every step they get the quantitative purification required only at the last stage, that is after protection, making the keto. It is a green and safe. It reduces a lot of byproducts. And for this innovation, they got the Green Chemistry Challenge Award in 2006. Another example I have put the sitagliptin. The chemical synthesis, there are a lot of chemical synthesis are reported in the literature. I have put the one of the best chemical route which initially industry has tried. It starts from the trifluoroacetic acid. The reaction with maltodextrin acid to get the maltodextrin atom, followed by the reaction with triacid to get the diketone, and followed by the reaction with amine to make the imine, and followed by the reduction to get the sitagliptin racemic mixture, and then next stage, resolution stage. So a lot of wastage are generated in this particular route. Although many stages are giving good yield. Merck came up with the better solution. It's a molecule of Merck. The previous team was also from the Merck. Merck came up with a better solution. It developed a chiral catalyst to reduce the immune selectivity, and they improved the overall production, overall conversion, and they got 97% E. And for this particular innovation, they got the Green Chemistry Challenge Award in 2006. Merck and Codexis, they did not stop here. They kept innovating again and again, and they find out a much better solution. The overall chemistry remains same. The ketoamide is prepared using the same route. Instead of the chiral synthesis, they used an enzyme, and the enzyme is such a selective, it gives 100% selectivity, 100% chiral purity, and around 95-97% conversion in the reaction. I myself tried this particular enzyme from the Codexis. I had an IF with the Codexis, and it gave reproducible results. And it has a biggest challenge. Codexis has made this enzyme protected in such a way, people are struggling to come out from that period. Although people have started making enzymes, infringing enzyme is available, but non-infringing enzyme is very challenging. We have other enzymes other than Codexis, but we are not going with that because of the protected. So I already talked about this. Then there are greener technologies. So one of them is the flow chemistry. Pharmaceutical industries in cases have used the batch manufacturing, which involves large equipment, costly product setup, high quantity of reagent handling, multiple steps, and lengthy process of manufacturing. Recently, industry has seen paradigm shift from batch manufacturing to continuous manufacturing, which is much faster, safer, and more efficient. All the stages which are part of synthesis of API to drug product, from synthesis to downstream processing to continuous crystallization, drying, blending, granulating, and tableting are possible in the flow mode. What is the difference between the batch process and flow chemistry? In the batch chemistry, we are used to do this chemistry from century. All the reactants are added, reacted, and isolated discretely. All the reagents are mixed up together, then we allow it to run for a certain period of time after completing the reaction, we take it forward. While in flow chemistry, we add reagents, we react them, and isolate them immediately. And it gives us a lot of benefit. challenges, but I will be positive. Being a positive mindset, I will talk about the best advantages of this flow chemistry. It requires smaller footprint. Around 1 to 2% area is required compared to the batch process. It can increase the product quality. Where you are finding that there is a possibility of impurity formation, we can reduce by using this flow chemistry concept. I will present 1 or 2 examples where you can find out this is possible. Challenging reactions which are not possible in the batch mode can be easily done in the flow chemistry mode. Like liquid gas reactions are easily can be done. By nature, the flow chemistry are safe. For example, you think about the reaction like trinitrophenol is being manufactured in a 10-gallon reactor, and something goes wrong, and you imagine what will happen. While the same footprint in flow chemistry is 1 to 2%, it is easy to contain, it is easy to control reactions. Flow chemistry are faster in nature. For example, we are doing reaction in solvents, like dichloromethyl. We cannot increase the reaction temperature beyond 40 degrees in a batch mode. While we can increase this temperature in flow mode, we can go up to 50, 60, 200 degrees, whatever we want. Just we have to apply the back pressure. And we can increase the reaction. How the Arrhenius equation says that as we increase the 10-degree reaction temperature, the reaction rates doubles. So reaction becomes faster. Anatomy flow reactor system, we need a delivery system, we need a pump, we need a mixing equipment, we need a reactor where the reaction takes place, we need a catching device. If the reaction is to be done under pressure, we need to apply a pressure regulator, and then collection vessel. And then further work. At Sun Pharma, we have a very good setup of equipments and laboratories. We have all kind of advanced flow reactors like agitated cell reactor, fixed bed high pressure reactor. We can go up to 100 kg pressure. We have Vapotec, we have Chemtrix, we have warning reactors, we have Miprova. Even recently we have purchased Stories Sabre sterile agitated buffet reactor. RVR also we have recently procured, and we are using that equipment for making peptides. Through flow chemistry, many reactions are possible which are difficult, like oxidation reaction, butylated reactions, reductive amination. Reductive amination, alkylation, hydrolysis, Grignard reactions, nitration, halogenation, rival reactions. These all can be easily done in the chemistry. Case studies. The first case studies I have taken is the oxidation reaction. It is the sulfoxide is being prepared from the sulfide. During the reaction, the over-oxidation happens and sulfone forms. If we do this reaction in batch mode, we can never stop making sulfone impurity because the product is also in the flask and the oxidizing reagent is refined, and we cannot stop the reaction till the time the reaction completes. So over-oxidation can happen. But in flow mode, this can be easily overcome. We have to pump the starting material, oxidizing agent into the flow reactor. And as soon as the reaction gets completed, we can immediately quench. So the residence time is such a low in flow chemistry. It are normally 2 minutes to it's from seconds even, from seconds to a minute. And as soon as the product comes out, it can easily get quenched using the reducing agent, and we can avoid the sulfone impurity formation. We scaled up this molecule, and it is in the continuous when we use the PFR reactor for this, and we got a lot of benefits out of that. Another example is the alkylation reaction. In this particular reaction, the pyridine and butadiene are pumped together, and then at a certain stage, the starting material is pumped and followed by alkylating reagent to get the final after cleansing to get the final product. This is an example of simvastatin. We successfully scaled up this reaction. In the reaction, in the batch process, the reaction required for this butadiene reaction is -75 to -70 degree. This can be easily done at 10 to 15 degree. The reaction time in batch mode 3 to 4 hours, it can be less than 9 minutes. We got marginal improvement in the product conversion from 70 to 89%, and we want to replace the THF already problem. So these are the benefits we got from this, and this also we have scaled it up. There are challenges as well. This is the lab reactor corning, and this is the commercial equipment where we have scaled it up. This is third example which I have took is carbonate formation followed by the hydrolysis. In this particular case, we pump the chloroformate type of reagent and the amine together, and in another pump we pump water and caustic solution. The alkylation takes place in the first coil, and in the second coil we pump another solution to hydrolyze the esters, and finally we get the product in a single reaction cycle. So, two chemical transformation happens in a single reaction cycle. This particular reaction also scaled up, and we got a lot of benefits using this flow chemistry. We have reduced the solvents drastically. We have changed the pyridine base from NOH. If you do the same reaction using NOH in the batch mode, you will end up only 40% product. You will never get the desired product. But this is possible in flow because of the nature of the chemistry, nature of the technology. Then there are continuous extraction using centrifugal extraction is possible. So challenges in batch mode are aqueous reduced residual impurity which needs to be removed using organic phase extraction. Multiple extractions are required to follow by water and brine washing. Lengthy process leads to product degradation and loss. By using this particular technology, we have reduced the usage of solvent, and single extraction we are able to extract the same product. Less time consuming, leads to less degradation, and process cycle time also reduced. I will skip this small explanation. So to summarize, green chemistry seeks to address the key issues of chemicals in the environment. The pharmaceutical industry faces a number of challenges to meet the aim of green chemistry, primarily due to molecular complexity of most medicines. As I said in the previous slide, first slide, by nature the pharmaceutical industry are complex. Significant progress has been made since the inception of green chemistry in early 90s. Green matrix information helps to understand process, highlight opportunities, and monitor improvement. Green chemistry matrix I have not explained here. Like in one of the slides I have mentioned E factor. So those type of calculation can help us and can overcome. Solvent have the biggest impact. Solvent 90% weight by weight is used in the one product. So what is future? Continued elimination, substitution of hazardous solvents and reagents toward that. Integration of chemistry and technology like flow chemistry and other chemical advantages which we can use. Application of continuous processing, development of materials from renewable feedstocks, development of new cleaner reaction and methodology, finding a clean replacement for toxic reagents. So these are our team members. Few of the team members were busy in technology transfer activity in various times, so they are not in part of this picture. Thank you.
reactions in flow chemistry?
Flow chemistry by nature, it has a efficient heat transfer capacity. So the volume, if you compare to batch mode, the area which required for control the heat is very less in batch mode compared to the flow mode. So volume with respect to the area which is required for the heat transfer is very high in flow chemistry. So that is the key benefit for the flow chemistry. We can quickly heat the reaction mass, we can quickly cool down the reaction mass, and you will find very less, blind spots, which normally happens in the batch mode. When I say blind spot means, visually as a chemist we cannot observe that there are some pockets where the heat is different in one location of the reactor and it is different in another location of the reactor. This is not case with the flow chemistry.
So but we can't able to maintain the operation conditions.
We can easily maintain the condition. See, a lot of technologies are available. Because the size of the flow reactors are small, advanced equipment we can apply to that. A lot of heating, cooling circulators are available, which can you can cool down to minus 100 degree to 300 degree and even beyond that. In batch mode, because of the size of the reactor is so high, and the area for heating or cooling is very less. We cannot, do the same thing which we are doing. You can do in a flow plant.
So in what way that the minus 100 degree Celsius will commercialize in industries?
Minus?
Just maintaining minus 100 degree Celsius is commercial in industries.
Yeah, normally batch mode we are using liquid nitrogen. But flow benefit is that the reaction which is required at low temperature in the batch mode, you can do at higher temperature rate in the flow mode, because the exposure is with very limited time period. I have one example. In one of the molecules, the reaction time is just 2 seconds. The same reaction if you are doing in the batch mode, you cannot control that reaction. Although we are using liquid nitrogen. Okay. But in flow mode, it requires only 2 seconds. So the same reaction which is required at minus 75, minus 95 degree temperature, we can do it at minus 30 or even room temperature in flow mode. Immediately the reaction mass is coming out, immediately you can quench it. So, a lot of technological advances.
Thank you, sir.
Good evening, sir. This is Dr. Ilhan. I lead flow chemistry company. So, at what scale commercialize this flow reactions and how many products you are commercializing?
Some information I cannot disclose, but I can say like that. One of the product we are manufacturing around 40 ton per year. So that particular example I have not added here. All these 3 examples I have shown are already scaled up. Yeah. So one of that I have shown the Corning reactor. So we have one lab setup and the similar setup we have at the commercial. It's a Corning G4 reactor.
So this method is that whenever there are safety issues in the batch photos,
yes, the biggest benefit of flow chemistry is like this thing. It reduces the safety hazard. So wherever there is out of control reactions are being done in batch mode, they should be tried or they should be transferred into the flow mode. And that is what industry has started doing.
Sir, have you tried any biocatalytic reactions using the flow chemistry?
I have myself personally not tried, but that is being done. By me. Using immobilized enzyme. So one of the slide I have shown you the fixed bed reactor. So similar kind of reactor are used in the biocatalytic reactions. Even RBR type of reactor can be used, rotary bed reactor, where you can add your immobilized enzyme into that reactor inside the coil, and you can do the reaction. In fixed bed reactor also you can do the similar kind of reactions.
Okay, thank you.
Dr. Bhargav, this is Madhusudan Ionics engineer. You mentioned that RBR, you are using RBR.
Yeah, one of my colleagues is present here. He is working on this.
Okay.
We recently bought, and it is Chennai facilities.
And did you employ the flow chemistry RBR?
No.
That is
RBR is a different set of principle. I think my colleague will explain that better.
So,
It's
flow
just
chemistry you can't integrate RBR.
Pardon?
Flow chemistry can be integrated with RBR.
Dr. Emil will respond to that.
Okay. Thank you.
I will come back to it.
Thank you, sir. Now moving next to hear from our chief guest, Dr. Emil Strong. Before I invite, may I request Mr. Kupaswamy to please come and say a few words about Dr. Emil, please.
Welcome Dr. Emil B. Strong, CEO Spinken, Sweden. It's my pleasure again to brief the audience about Dr. Emil's professional journey. And this is his third visit to India. He loves India. Dr. Emil B. Strong is a highly experienced CEO and chemist with expertise in research, product development, marketing and sales. He is all in one. He currently serves as CEO of Spinken AB in Umeå, Sweden, where he is responsible for research, product development, marketing and sales. Prior to this, he worked as a product manager at Nordic Chemcost AB, where he conducted research and development of polymer-supported transition metal catalysts for organic synthesis and managed the product development of technical solutions for solid-phase chemistries. Emil B. Strong is also the founder and owner of eBiz AB, a consultant firm in Umeå, Sweden, where he provides innovative technologies and consultative activities with a focus on polymer chemistry, material science and adjacent areas of technology. As a chemist, Emil B. Strong holds a PhD in chemistry from Umeå University, where he focused on the synthesis, functionalization and characterization of porous polymers materials for chromatography. Throughout his career, he has also worked as an expert advisor for the Transboundary Water Project in Lithuania and Belarus, where he provided quality control of government-controlled laboratories in Lithuania and Belarus and their analysis of water quality parameters. He has also developed a multi-channel fiber optic based instrument for the determination of dissolved oxygen in water, including software for data acquisition, signal treatment and report generation while working as a chemist in Umeå Marine Services Center. Emil B. Strong background is research and development, coupled with his expertise in polymer chemistry and material science, make him a valuable addition to any research project developing new treatment technologies. His experience of managing product development, marketing and sales also demonstrate his ability to lead and contribute to multidisciplinary teams. Thanks for accepting our invitation for this seminar. Traveling far off from, he has traveled the globe now for the last 10 days, far off from more than 10 to 15,000 kilometers, now far from Umeå he went to US, from US he went to Japan and he is going back to his Umeå after a gap of 15-20 days, I think so. And we want to call this as RBR, where it is rotating bed reactor. But I bet after listening his talk, all of you will call this as rotating brain reactor, because this will rotate your brain. You will start thinking where all this can be applied. And the RBR is on display today here. Everyone I request to take a look when you are here. And we have done hundreds of demos throughout India, pharma, non-pharma, and other companies also. And many challenging process reactions can be tried in this. We have attended many queries, like from reducing the reaction time from 16 hours or 19 hours or 18 hours to 9 hours or half of the time or 1/4 of the time, and also carbon treatment. There are many areas we have done the demo, and we have got very good installations, and many people are looking us nowadays for more number of systems or for other challenges they are facing. That's why we arranged this seminar. Thanks for attending this seminar. Dr. Emil Bismarck.
Thank you very much for that introduction and for having me here. I would like to get an overview or give you an overview of this technology and what we're doing in a lot of different fields. We are active not only in pharma but also in nuclear and food and beverage and so on and so on. So I will drop by a few different industries and we'll see if we end up. At SpinChem, we believe in a world where industrial waste is no longer a problem, where the oceans are clean and the air is pure. This is everything where we come back to when we decide which type of applications we're involved in and what we are doing. And this is because we are in north of Sweden, and I will give you a few examples of what we're actually doing in this sustainability, collaboration, and what we can do together with innovation to improve the environment. So ongoing development with customers and partners. One is to remove the carbon dioxide from the air at the same time as we are restoring the ocean. I will not get into the details really, but you can take the carbon dioxide, convert it into a more stable form at the same time as you're preventing the acidification of the ocean. You can store the carbon dioxide in the sea. It's the biggest sink of carbon dioxide we have in the world, so let's use it even more. We have a challenge to get more lithium. A lot of electrical cars, and I don't feel that I would like to drive a car where we have kids in the mines or extracting metals from the earth in a non-sustainable way. So we are involved with a US company to use the rotating bed reactor to extract lithium from brine, a salt solution from the ground in South America. So this is a future application, and these type of applications is exactly what drives us to continue to develop the technology. We are located far north, in northern part of Sweden. So you see a blue pin on the top of the map. It's the Arctic region or the subarctic region. So if you would like to run reactions at -100 degrees, it's almost what we call room temperature, not really, but this is how it could look like. This was earlier in January when I was out skiing, minus 38 degrees. My ambition as a CEO of the company is that I should not longer be needed in running the company. It should run itself. So this is the greatest inspiration for me, and where I do the reflection, develop the new solutions, getting out in nature, relaxing from work, and processing all the thoughts. So I really encourage you to, if you're not doing yoga or hiking in the forests or so, that's where you really solve the problems. According to German scientific study, in brainstorming sessions, 1% of new ideas came. In dinner time, about 11%. During boring meetings, about 7%. If you have an interesting meeting, much less than so. So in nature, 27% of the new ideas come when you relax from work. We have 49 patents on this technology in a lot of different countries based on the 8 different families. And if I interpret your talk about patents, you all have to buy a rotating bed reactor to be able to file new patents on new processes. Is that right? Great. We have 220 customers in 35 countries, and some customers we are really proud to have. Of course, all of them, but someone are standing out a little bit. 2 of them. Frances Arnold. She bought a system from us in 2018 in March, and she got awarded the Nobel Prize the same year for the directed evolution of enzymes for biocatalysis, essentially. Benjamin List, he bought a system from us in March 2021. The same year, he got awarded the Nobel Prize. So you see now the trend every 3rd year. So we'll see now what happens 2024. I have the customer list from March, so I know some future prospects. If we should follow the trend, it developed asymmetric organic catalysis. It looks like it should be something involved electrocatalysis or photocatalysis. If you look at our customer list from March, so we will see. I will update you. If we look around, or if I interpret well what we have heard now about green chemistry and so on, we need more sustainable solutions and efficient solutions, both in the chemical processes and purifications and so on. And we are focusing particularly on biocatalysis, but also adsorption reactions, chemocatalysis, and solid phase synthesis. I will get a few overviews, but on a very high level.
The core foundations of heterogeneous processing of large liquid volumes are going through massive changes. A transformation, you might say. The reason is the spin chem process rotating bed reactor. The Pro-RBR enables faster and more efficient biotransformations using immobilized enzymes, and is also reducing process time and minimizing the amount of resin material needed in decoloration and other absorption processes. It can be implemented in a batch mode configuration directly inside a process tank. The spinning motion generates a strong convective flow of created are strong enough to drive the flow of liquid without external pumps. After processing, the flow can be directed back to the original tank or to additional reservoirs, creating a continuous flow process. To maximize mobility or gain access to strongly contaminated areas, the unit can be mounted on autonomous vehicles, covering vast areas. All in all, the view of processing large liquid volumes has forever changed. And in the center of the transformation stands the SpinChem Pro RBR.
So maybe that answered one of the questions on how to implement this in a flow mode. We have done this in a few different setups, and I might come back to that also more. But otherwise I can show other movies as well. I could spend the whole day, or at least 5, 6, 10 hours talking about different comparisons with different technologies and the rotating bed reactor. I will show you this graph first, just to give one example of the benefits, where in this case it's a 1,000 liter tap water deionization ion exchange process, just to show and compare the same conditions with the same amount of material and how it could be implemented with the rotating bed reactor and cut the processing time and make it 3.7 times faster. This is one example, and we have many more. It's not always faster, but sometimes it is. Most often it is. So other benefits also include the simplicity of the scale, long catalyst lifetime, and it's very easy to automate. No filtration is required, and there are also other benefits that comes with this technology. In one of the processes, in a 100 liter reactor in US, they could cut the reaction time more than half. This is just one example, and there are many more. We're also involved in other type of developments. Since environmental applications is really close to our heart, and the reason why we are involved in these different industries is what we learn in pharma, we can take back and implement it for treatment of leachate water to remove polyfluorinated compounds in contaminated soils. What we learn from those setups, where we run 120,000 liters a day, continuous 24/7, we use that in the nuclear industry. And what we learn in nuclear industry about scale, we can bring back to pharma. So, since the technology is very versatile, we can learn from all different types of industries, and especially on a regulatory basis, and how to keep traces of material and so on, is very similar across all the industries. So in this project, we're not only capturing the PFAS, we're also destroying it using a combination of electrochemistry and adsorption processes and other type of foam fractionation processes. And as I have been mentioning, we are on a mission to reduce the radioactive waste in the world. Fukushima, you have all heard of. You still know that the waste from the development of the atomic bombs since the 1950s, both in UK, in Canada, and in US, and other places in the world, where all have the race about who could develop most atomic bombs. They also created a lot of waste. That waste is now stored in tanks, in ponds, everywhere, and they have started to leak. Since the design life of those tanks were only maybe 10 years or 20 years, and now it's 70 years old. So we have a huge problem with radioactive waste. And now we can take the rotating bed reactor technology and bring in and take away those radionuclides where they are. You don't need to remove the liquid. You take care of the radionuclides instead where they are in situ. So it's a huge benefit from a work health perspective, because then workers can get in there and take care of the real waste, which is on the bottom of a pond, for example. So this very much resembles to what we can do now in pharma industry also. So this unit, it's a 14-liter rotating bed reactor, and it's been used to treat a 95,000-liter tank. So you open the lid, you put in your specific media that you would like to have. In this case, we had cobalt and the cesium-specific media. And when we lower it in a tank and you start rotating it, you will throw out the liquid inside and suck new one in. So with a small unit, you can affect a really large volume. In this case, we took care of a 25-year-old problem of a tank stored in the basement of a nuclear power plant, and we could reduce the waste from 95,000 liter into 56 liter, and for final storage in a drum. So this is one example of how the scale could work. That unit was actually designed to remove pesticides from vegetable oils in a 500-liter batch mode. Now we used it in 95,000 liter. So you can see that the scale depends on your application. How effective is your catalyst? How effective is your adsorbent or the ion exchanger? So you don't need to tune and make bigger and bigger and bigger units. It's about using the selectivity or the catalyst efficiency. So we already had a little bit of an introduction on the biocatalysis, which is our most important field. By far, most pharma companies that buys our products are using it for biocatalysis. One of such development projects that we are involved in now is to build the first enzymatic plastic recycling facility, where we can, together with the customer, take the enzymes, break down the polymers, and use those monomers that you have as building blocks for new polymers again. So you have an infinite recycling loop. It's not about incineration and so on. It's about really do the recycling so that you can reuse it, and we don't need to dig up any more fossil fuel to still create plastics. So the way this works is that you take the genetic code of a bacteria and you program that to meet the specific needs for a certain protein to be excreted by the bacteria. And then you go into the lab and you immobilize it and make a biocatalyst out of it. Maybe you have to do it a few cycles or a couple of thousand cycles, and here AI come into play, and you can really optimize the enzymes in a really efficient way. So this is also used in another project where if the customer succeeds, it will be a really interesting application where they take flue gas the carbon dioxide emissions from a factory, and they pump it down to a chemical reactor where you have a rotating bed reactor with a special enzyme to convert carbon dioxide into cellulose fibers. And you can actually do textiles from the carbon dioxide. I think this type of ideas and more or less to do photosynthesis in a very efficient way. We have partnered up with 5 other companies to be able to provide the same thing as Codexis have done. Since Codexis more or less abandoned the biocatalysis field just a few months ago, that they will focus more on vaccines, I think. There is an open space. And we always would like to team up with smarter people than ourselves and to have experts in special settings so that we together can accomplish all the way from a sequence and doing the enzyme discovery, enzyme engineering, scale up and process development, and then together with Allozymes in Singapore, Aminoverse in Germany, Chiral Vision in Netherlands, Candidum in Germany, and Enzymicals in Germany, and Spinchem in Sweden, we can provide you all the way from an idea. You just give us what molecule you would like to do, and together we can deliver the full-scale process in a cost-effective manner as well. So we have been working with Chiral Vision for a really long time. They are by far the best people in the world when it comes to enzyme immobilization. And by doing this and immobilizing the enzymes tuned on the specific carriers, they get really stable enzymes, and they can recycle them over and over and over again and run them for weeks, months, years, depending on the application. But we're also in a project together with the Technical University in Eindhoven, Technical University in Delft in Netherlands, and the University of Bielefeld in Germany, together with Chiral Vision also, to develop new routes using biocatalysis to produce non-natural amino acids and use those in solid phase peptide synthesis. So we're both developing new reactor types, but also new routes for the building blocks. In a short summary, since it's a little bit cut in the end there, but what we play with is the mass transfer, the transport of the liquid to the solid. And the faster you go with the rotating bed reactor, the less of mass transfer issues you will have. Until you reach the limit where mass transfer is no longer a problem, the reaction will plateau out, and hopefully you have cut enough time and you can recycle the catalyst and so on and so on. As you see, collaboration is what we really would like to do. And we also would like to collaborate with you, with Indian companies, to develop new processes and so on. We also have a lot of different collaborations with academia. We are still a small company, but last 5 years we have had more than 75 students doing project work with us, because we have streamlined the process in bringing in students, letting them do whatever they want with guidance on a specific framework, and both the student can grow and we can try new things that we don't have time to do ourselves. So most of the products that you see have been student projects in 1, 2, 3 different projects maybe before we release it as a product. So then we have a close collaboration with academia, and like in this also in European Union, where we get a lot of money to hire PhD students. So in 2 different projects we had in total 25 PhD students. And together with Roche, BASF, AstraZeneca and so on, we can have these PhD students to develop processes for us. And it doesn't cost us anything. That's the best thing of 2 worlds, I think. Or at least for us and the students. So, where I would like you to start is with the starter kit. So this is what we have on the stand here as well. Essentially, you have a glass vessel, a reactor holder, a lid, a shaft guide, a motor, and together this becomes the complete starter kit, S2 and S3. If we remove the stand and the motor, you have the mini starter kits. So this is the best way of getting a plug-and-play system in your lab, and then we are willing to support you and develop the processes with you and be a part of the journey to the scale-up. More than 80% of our revenue comes from returning customers. So we know that if you start with this, you will come up with new ideas, new applications, and we can develop together. So to leave you with something useful, if you would like to dig into biocatalysis, we'll tell you about the last project that we're finishing off now next week, where we are using bio-based resources and biocatalysis to do biopolymers. So essentially taking nature and turn it into plastics that you can also recycle. So this has been a project together with Henkel, the world's largest adhesive manufacturer in Germany, and GlaxoSmithKline and Purolite, to develop new carrier materials and new proteins, assemble them to heterogeneous biocatalysts, and scaling up processes. So what I would leave you today is a free course that we have done together, all these partners. It's about 10-15 European top professors in the field of biocatalysis, and we have made a free online course that will be released next week. So I will get the link to Gopaswamy. He can send it to you as a follow-up from this seminar, and you will have 18 hours of free movies to watch on Saturday night. It's an introduction of both sort of the mindset of sustainability, but with a prime focus on biocatalysis. We are here to help you and assist you. The people you will probably meet in meetings, if we set up digital meetings from Sweden, is either me or Eric. And whatever type of questions you have, I'm willing to answer now or in a later meeting. So please shoot. Any questions?
It is good what actually presented. I would like to appreciate the RBR and your associations with the different organizations all the globe. So in the liquid phase it is fine, but when it comes to the viscous or some more high density phases, so what would be the mass transfer issues?
A rule of thumb, the more viscous, the longer time it will take, but it will still work. So pure
mass transfer.
Yeah, it will be improved. I mean, things that you can't pump through a column, like if you take pure glycerol, it will be a pain in the neck to try to pump that through a packed bed. But it will work in the rotating bed reactor. So if you're doing decolorization of oils or reaction in viscous media, no problem. But the thicker it is, the longer time it takes. It's very proportional.
So hello, this is Pramod from Natko Parma. Very nice talk. And you briefly mentioned about the peptide, and you have not elaborated much, but I would like to understand that. So could you elaborate a little bit about how the peptide chemistry is done in this rotating bed reactor?
It's a simple reason why I can't share anything. Because we were working together with a few different companies that are developing peptide synthesis routes. It's still in lab scale or up to 14 liter of solid phase. That's the largest that we have done. Well, our ambition, or what we have been proving, is that we can, with the special designs of the reactor vessel, together with the rotating bed reactor, we can greatly improve the use of solvents. So you can decrease the amount of solvent. We know from other type of applications that we can significantly cut washing times and the amount of solvent used in washings. But I can't share any data or so right now. We have more people working on the solid phase peptide synthesis. It's by far the most interesting area now if you just look at the FDA list of approved drugs, of course. So we are happy to collaborate with everyone that would like to be part of this journey and scale up synthesis.
Okay, and then there is another interesting molecule is oligo. Any plan of working on that field?
I mean, it's the same type of processes, more or less. Yeah, we are doing whatever our customers ask us to do, more or less.
But yeah, this peptide chemistry is, I would say, that more robust and optimized when we compare with oligo.
Yeah.
So, considering that the moisture contained and all these things matter a lot.
Yeah, but there are workarounds and possibilities for sure. It all comes to how can we produce the purest compound with the highest yield in every step. Yeah, that's a really nice technical challenge, and we're willing to jump on that one. Any other question?
Yeah. Hi sir, this is Maharshi from Dr. Reddy's. So if you wanted to implement RBR in our development, I mean process development, what are the scale of parameters we need to consider from lab to pilot scale or commercial scale. If you are using RBR in the lab, so what are the scale-up parameters we need to consider?
It's all about the solid to liquid ratio. How effective is your catalyst or adsorbent and so on. We do simulations and can have a very good idea about the total flow rate through the rotating bed reactor at a given RPM. So the loading in the rotating bed reactor, I don't think I mentioned that you don't need to fill it completely. So you can have a large RBR or a small one, and the amount of loading will greatly influence the parameters that you're talking about. I mean, essentially what you would like to have is the same reaction time in 200 milliliter as in 20,000 liters.
Yes.
And in the nuclear example of the 95,000 liter tank, we were running the lab scale tests in a 20 liter bucket, and we got exactly the same result there as we got in the 95,000 liter later on. So it depends on your process, and we can give you an idea on how much longer it will take or which parameters to look into, but rotational speed is one, viscosity as we mentioned, loading and so on.
Okay. Thank you.
Do you think we can apply this for the sewage treatment also?
Sorry, for
sewage treatment? Sewage treatment?
sewage treatment. Yeah, in theory, yes. The reason why we haven't done that yet is because of the too large scale and no one that is willing to pay. To create a sustainable business, we also need to earn some money to be able to put it into new processes and develop new technologies. But the only sewage treatment project that we have been involved with is with NASA and the university to take care of the sewage at the Mars expedition, where they take the poo and they incinerate it at high pressure and high temperature to make activated carbon to then purify water on the planet. So that's science fiction for for the next Neo Hub magazine maybe. So we'll see in the future. No more questions. Let's finish.
Thank you, Dr. Emil, on taking the questions and clarifying the doubts and educating us more on the RBR. Thank you very much. Now, moving on, we would like to honor the guests with the little token of the gift. May I invite Mr. Satyaprasad to please come on the stage, please. May I invite Dr. Padmaja to please come. And I request Dr. Bhargav to please come. And Dr. Emil, please. This will be for Thank you, sir. This will be followed by a little note of vote of thanks by Kinara.
I requested you to have a look on the RBR for display here, and it is installed in our application lab in Balanagar, and we also give the RBR for your trials in your laboratory on rental basis. You can take it and you can establish your POC. And we have given this to several companies. They have benefited out of it. I wanted to inform the audience. That's it. Thank you very much.
Very good evening. This is Kinara from Smart Labtech. On behalf of Smart Labtech Private Ltd, it gives me an immense pleasure to deliver the vote of thanks for this great event to all dignitaries assembled here. Our hearts are filled with lots of gratitude and respect for our distinguished guest speakers, Dr. Emil Bistrom, Dr. Bhargav Pandya, Dr. Padmaja, for not only sparing their valuable time for us to grace this event, but also enlightening us with their commendable and exemplary talk on the subject. Next, I would like to thank our respected delegates for accepting our invitation and making a grand success. This vote of thanks would be largely incomplete without expressing my gratitude for the other staff members who have been working really hard and carrying all the duties very diligently. I would like to express my sincere gratitude for hotel's exceptional hospitality and service during this event. Thanks to the photography team who has taken beautiful pictures of today's event, which would ensure beautiful memories of this program. I sincerely apologize if I missed out somebody inadvertently. Thank you again, all of you. Have a great evening.
I request all of you to have a look at this RBR and then proceed for the dinner. Thank you. Good night and take care. Bye-bye.
Good job, sir. Good job. Yeah. I think we had a discussion with him now. Thank you, madam. Thanks for coming. Just a brief from
the glass is the limitation, so it's 230 degrees is the It's slightly acidic, yes. It's acid resistant stainless steel, so it will last. I think, if you're doing trials,
go up to 1500 RPM. In this we can go up to 1500 RPM. इससे क्या होता है कि रिएक्शन टाइम जो है वो reduce लिक्विड से और सॉलिड कॉन्टैक्ट जो है वो ज़्यादा इसमें रहेगा, इसलिए आज ये अगर लिक्विड है ना इसी टाइम ऐसा फिटिंग होता है।
ऑटोमेशन हर बैच में डालना निकालना बाकी कैटलिस्ट से हो जाएगा, उसमें कैटलिस्ट रिकवरी बहुत ज़बरदस्त हो जाएगी।
वो बीच में भी क्या होता है
वो टकराएगा, फिर वापस वोर्टेक्स जैसे फॉर्म होके, अभी देखा ना सर ऐसा फॉर्म होके फिर से उसकी चैम्बर को आई विल डू
एट शेप.
आपको कम भी होना है तो वो कैप्सूल साइज का आता है.
Based on catalyst size.
हाँ कैटलिस्ट. बेसिकली विल होगी वन ऑफ
इसमें सॉलिड डाइजेशन.
हाँ इसमें सॉलिड करके आपका नॉर्मली 8 आवर्स इसमें क्या है कि वो यूनिफॉर्मिटी जो रेजिन डालते हैं वो रेजिन में घूमते रहता है, तो उससे में क्या होता है कि ज़्यादा रिएक्शन होता है. इसमें क्या होता है कि ये वोर्टेक्स फॉर्म होता है, ये ग्राफिल अंदर का प्लस कहते हैं ग्राफिल